to calculate the density of allowed quantum state. Okay, so now see here, we will take what we will now we will place the allowed quantum state. Okay, so now we are trying to place what allowed quantum state in two dimensional. Okay, two dimensional space, that is ky and kx, ky and kx. What we are placing? Two dimensional array. We are placing that two dimensional array of what allowed quantum state, okay, which as a function of kx and kx and ky. Okay, so these are my what two dimensional allowed quantum state. See here, allowed quantum state. So these, okay. These are what? These are allowed quantum state. Yes, allowed quantum state. These are number of allowed quantum state. Okay, as a function of kx and ky. Okay, so corresponding to each, corresponding to the integer value of nx and ny. Okay, corresponding to integer nx and ny. Okay, so if we see here kx, so this is my resultant vector. Okay, vector k space. This is my resultant, and this is like differential k space. Okay, differential distance. Okay, remember this k space direction, this distance is nothing but, in case of sphere there is a radius. Radius vary means spherical sphere, size of the sphere will vary. Okay, like here only, if this k space vary, if this k vector vary, then this two dimensional kx ky will vary. Okay, so therefore two dimensional space will vary. So now these are the distance between two quantum state. Okay, so let us say this is my kx and this is my kx plus 1. This is what distance between the two quantum state. What we are doing, we are actually plotting what allowed quantum state in two dimensional space. Okay, two dimensional space. Okay, so because we have extrapolate the one dimensional into three dimensional. Okay, one dimensional what? One dimensional infinite potential well, result of one dimensional infinite potential well into what? Into this three dimensional k space. Okay, three dimensional k space. Then we are just plotting what? We are just plotting what? Plotting the two dimensional array of allowed quantum state. These are what? These are allowed what? These are allowed quantum state. Okay, so these are my allowed quantum state. Okay, so these are my allowed quantum state. In two dimensional plot as a function of kx and ky. Distance between two quantum state is what? Like kx and kx plus 1. Okay, so now if we want to determine the density of allowed quantum state. Okay, so the density of allowed quantum state, in order to determine the density of allowed quantum state, we need to consider here by considering. Okay, so the density of quantum state is determined by considering only what? By considering only, see here, this is my what? Cube. Okay, we have seen this. Okay, so we have seen this is my cube. Okay, so this is my cube. Now there is how many corner? 8 corner. How many? 8 corner. Okay, so these are my 8 corner. I am taking only one corner. Okay, one corner out of 8 corner. Okay, this one corner is what? Like this. Okay, so this is my x-axis, this is my y-axis, and this is my z-axis. I am taking only one corner. Okay, so this is my kx, ky, and kz. Okay, so this is what? Positive value. All positive value of kx, ky, kz. I am taking 1/8. Okay, out of it only 1/8 I am taking. So therefore this is what? This is nothing but it is the volume. If you see, ultimately it is what? The volume of single quantum state. Okay, for single quantum state I am taking. Okay, so we are taking only for single quantum state. So this is what? How many corner? 8. Out of it we are choosing only one. So therefore the density of allowed quantum state is determined by considering only positive of positive 1/8 of positive value, positive 1/8 of positive value of kx, ky, kz. Okay, so now see here the distance. So this we have calculated. Okay, for single, this is kx, ky, kz. Okay, so now see, the distance between two quantum state is how much? So distance between two quantum state, let us say this distance is a, this distance is d. How much distance is there? Kx plus 1 minus kx. Yes, kx plus 1 minus kx, which is nothing but nx plus 1, nx plus 1 into pi by a, pi by a minus, okay, so minus nx into pi by a. Okay, so what we will get? Finding pi by a. Okay, so how much distance is there? Pi by a. Okay, so now we know very well what these are my quantum state. Okay, these all number of quantum state, distance between each two quantum state is how much? How much distance? Pi by a. Pi by a distance. Okay, so pi by a distance. Pi by a distance. Pi by a distance. Here is also quantum. Here is also quantum state. Allowed quantum state. Allowed quantum state. This is pi by a. This is distance d. Distance d. Distance d. How much? This distance is what? This is d. D. Okay. So this d is what? Pi by a. Distance is what? Pi by a. So then in, so like this, therefore what is the volume? Okay, so we are considering only this for single quantum state. So therefore what is the volume of, what is the volume of, what this, for this single quantum state? This is nothing but a dq. This is nothing but dq. Okay, so this is what volume, so which is nothing but pi by, which is nothing but pi by a whole cube. Okay, so this is nothing but pi by a whole cube. This is what volume, what volume of single quantum state. Okay, single quantum state, we are taking what volume of single quantum state. Yes, yes, I hope you understood this. Okay, so this is what crystal, this is nothing but three-dimensional infinite potential well, which is nothing more than the crystal, just a crystal. Okay, so because we don't know for the three-dimensional how we can write this energy versus momentum equation, then what we took the help of what one-dimensional infinite potential well. Okay, so that we have drawn in the last class. Then after that we extrapolate this result. Okay, this result into this three-dimensional space with the help of this. First what we did, we just want to see in two-dimensional surface. Okay, so in two-dimensional, what in two-dimensional we plot what, we plot the allowed quantum state. Okay, array of allowed quantum state. Okay, we as a function of, as a function of kx and ky, this is what a resultant. Okay, resultant k space. Okay, so then after that what we did, we just select one, what, select one quantum, this one corner of the cube. Okay, so this, okay, out of 8, total is 8, out of 8 we took only one. Okay, we just choose only one. So then after that we calculate what distance, distance between what, between two quantum state. Okay, so this way we have calculated how much, this is vk is equal to pi by a whole cube. Okay, so now we want to determine what differential volume. Okay, so let us first determine differential volume, because in order to calculate the density of quantum state, we need the volume of the volume of the single quantum state, and we need the differential volume, differential volume of the quantum state, volume of the quantum state. Okay, so these all we want to calculate. Now we want to calculate the differential volume of the quantum state. So this is what, so let us see this is my kx. Yes, this is my ky, and this is my kz. Okay, so this is my three-dimensional. Okay, so just a three-dimensional sphere. Let us say this is my three-dimensional sphere. Okay, so now I want to determine what differential volume, what differential volume. So let us say this is my differential volume, what, dk. So this is my dv. Differential volume is how much? 4 pi, 4 pi, 4 pi, 4 pi k square dk, k square dk. So this is my differential volume. Yes, this is my what, differential volume. Now we have calculated what differential volume, and we have calculated volume of the single quantum state, which is nothing but pi by a whole cube. Okay, pi by a whole cube. And we have also selected one corner out of each corner, because in order to determine the density of quantum state that can be determined only by considering the positive 1/8 of the kx, ky, kz. Okay, so therefore see here the density of what, density of allowed quantum state. So this is what density of allowed quantum state, gt of k as a function of k dk. is equal to, we are seeing in what, in two dimensional k space. Okay, so gt of k dk is equal to how much, this is how much, so this is first 2 into 1 by 8 into what, differential volume divided by volume of the quantum state. Okay, so volume of quantum state. Now see here, what is this 2? This 2 is nothing but, this 2 is nothing but, because each quantum state has what, two allowed spin. Okay, each quantum state has two allowed spin. What, these are the two allowed spin, allowed spin. Okay, so these are the two allowed spin for what, for quantum state, each quantum state. This 1 by 8 is what, this is nothing but this is 1/8 of the positive, this is nothing but 1/8 of the positive kx, ky, kz. Okay, so because as we have seen, we have selected only one corner. Okay, one corner, by what, by taking and by choosing that we can determine the volume, we can determine what, the density of allowed quantum state. Okay, so this is up to this. Now let us see here, this is 1 by 8. Okay, so this is what, this factor is taken into account. Why? Because we have taken only the 1/8 positive of kx, ky, kz, and this two factor has taken into the account. Why? Because this two, because each allowed quantum state has two, what, two allowed speed, either positive half or negative half. Okay, so now this is my differential volume that we have calculated, and this is my volume of the, volume of quantum state, single quantum state. So therefore this gt of what, this gt of k dk is equal to what, dk is equal to what, 2 into 1 by 8, 1 by 8. Okay, so 1 by 8 into dv is equal to what, 4 pi k square, 4 pi k square. Yes, dk divided by volume of what, volume of single quantum state that we have calculated as pi by a whole cube. Yes, pi by a whole cube. So this is what density of allowed quantum state, quantum state in term of k. Now just put this value of k as what, as we know, 2 me into h cut square. Okay, so now replace this k value by this in term of energy. We will get what, we will get density of, we will get what, total density of quantum state. Okay, so let us see, I am going to rub this. Now you just calculate this, you just put this value of k here, and we will get what, we will get total number of quantum state. Okay, so we will get g of e de, g of e de is equal to 4, sorry, okay student, so this is what the density, what, density of allowed state. Okay, so let us see, if we will solve this, what we will get. See here, this is g of e d is equal to what, is equal to, this will give us what, 4 pi. So this is nothing but 4 pi, 4 pi into 2m, 2m to the power 3 by 2 divided by what, divided by h cut divided by h cube, what, h cube. Okay, so we will get this when we will put this. Okay, so this value of k. Okay, so this value of k, so when we will put this, then we will get this value into root d. Okay, so now this, see here, this d will get cancelled, and we will get what, total. So this is what, total density, total allowed quantum state. Okay, so g of e is equal to 4 pi 2m. So 4 pi 2m to the power 3 by 2. Okay, to the power 3 by 2 divided by h cube into square root of e. Okay, so this is what, this is my density of what, density of quantum state. This is total density of quantum state. Okay, total density of quantum state into what, this is what, cube. So this is what my total total density, this is my of total density of quantum state, allowed quantum state. Okay, so allowed quantum, allowed quantum state. allowed quantum state. Okay, so total density of allowed quantum state. Okay, from where? From from E to E plus D, E plus D. Okay, so in crystal space of volume AQ. Okay, so this is my total, what total density. So this is what total, not density, sorry. So this is total number of what? Total number of. This is my total number of allowed quantum state from E to E plus DE, E plus DE. Okay. Now this is what AQ is the volume of crystal. Okay, volume of crystal. Now, if I will divide this by what? Volume. Volume. Okay, we will get what? Density. Density of state, density of allowed quantum state. Okay, so finally, what we will get here, if we will see, these are my what? Total number of allowed quantum state from E to E plus D distance. Okay, so this much. Now if we will divide this total number of allowed quantum state by what? By volume, then we will get density of allowed quantum state. Okay, so now finally we have reached our ultimate goal of what? To determine the allowed quantum state. Okay, so see here, allowed quantum state. Now see what we will get. G of E is equal to what? G of E is equal to 4 pi. G of E is equal to 4 pi 2m to the power 3 by 2 divided by h cube into square root of E. Okay, square root of E. This is what? This is the state per unit energy per unit volume. Okay, per unit volume. So this is what? Density. This is what? Density of what? Density. This is my density of allowed. This is my density of allowed quantum. This is my density of allowed quantum state. Allowed quantum state. Okay, so this is my density of allowed quantum state. Allowed quantum state per unit volume. Per unit volume. Okay, per unit volume, or you can say per meter cube or per cube centimeter. Okay, so this is my density of allowed quantum state. Density of allowed quantum. This is what? Density of allowed quantum state per unit volume, or we can say per cube meter or per cube centimeter. Okay, so this is what? This allowed quantum state is for what? For free particle. For free particle. Particle for free particle. Okay, so now free particle in the sense means particle is outside, means we are assuming the particle as outside the crystal. Okay, so when we will take this particle inside the crystal, then it will become somewhat difference will come only in energy and in mass. Here mass inside the crystal will get affected, that we represent that by effective mass, and this energy will also get shifted by some amount in case of valence band and in case of conduction band. Okay, so now we will see further this density of quantum state inside what? Inside the semiconductor crystal. Okay, so this is the density of state for what? This is the density of state for free particle. Yes, for what? For free particle. Okay, so now we will see the density of state inside the semiconductor crystal. Okay, so in conduction band as well as in valence band. Okay, so now see, so this is up to this. Okay, we have reached our ultimate goal of what? Density of state function, which is nothing but density of allowed state. Okay, density of allowed quantum state per unit volume, or you can say density of allowed discrete energy state, or you can say density of what? Density. You can say density of allowed. You can say density of allowed discrete density of allowed discrete energy state in conduction band, or okay, so this is just for free particle. Okay, so discrete, this is density of allowed discrete energy state. Okay, per unit volume. per unit volume, or you can say per cube meter or per cube centimeter, depending on whether the volume is in centimeter, cube centimeter or meter cube. Okay, so this is all about the density of state function. Okay, so density of state either in conduction band or in valence band. Okay, either in conduction band or valence band. So that's all for this topic. Okay, so then we will come next topic, that is density of state inside the semiconductor crystal. Okay, so thank you.